In this video, we're going to pick up where we left off in discussing blocking and when we should and shouldn't use blocking and what blocking variables are. So we left off with some issues, and in talking about issue 3, we wanted to mention that sometimes we have a choice when it comes to blocking. That is, sometimes we can choose to randomize within different levels of a factor, or we could choose not to, depending on what our design is and what factors we're interested in. So in this case, we're studying laser etching equipment. We have operators as a second variable. We could easily assign the laser to the operator in coupons, so we could randomly assign this, but we could also randomize within operator, randomize the assignment of laser to coupon, or we could randomize operator to coupon within laser. So there's a lot of randomization choices that we can make here, depending on, well, for multiple things. It depends on a research question, it depends on the context, it depends on what's easier and what's harder. So all of these are reasons we may choose one way or the other, but all of these also relate to the fact that blocking variables and independent variables aren't necessarily the same thing. Again, blocking has to do with this additional restriction on randomization. If it's just an independent variable that we don't care about, that doesn't restrict randomization, we would simply include it in the model as a second independent variable, and not necessarily consider that to be a formal blocking factor. So that brings up a great question. When should you actually be using these blocks? Like, really, when should you use this? So one of the first ways or places where you should be using these blocks is when we have limited experimental units within each factor level. So think about with those metal ingots that we were talking about earlier. In class, when we had each of those different coupons cut out of a metal ingot. If we have a limited number of experimental units per ingot, that might be a good reason why we would choose to use that ingot as a blocking factor. Consider that if we could cut all of the coupons for the entire experiment out of a single ingot, we might just be able to do the entire experiment without ever having to change the blocking factor level. We could just keep it at that single ingot for the entire factor. Now, note a potential problem with this. If future experiments aren't going to be using that ingot, then maybe it would be good to try out several different ingots to make sure that those don't have a particular effect. So that would make ingot itself a factor of potential interest on the outcome, and we might want to look at that as a second independent variable, not necessarily a blocking factor. But if the ingot doesn't have enough coupons that we can get out of the ingot, so maybe we can only get 4 coupons per ingot, and for the study we're going to need 16 coupons. Well, if we're going to be using 4 different ingots, there's only 2 options. We can either account for the fact that we're using 4 ingots, or we cannot account for the fact that we're using 4 ingots. So when we have the limited number of EUs per factor level per ingot, that's a good time. So let's say we have to use 4 blocking factor levels. Well, we may as well include the blocking factor so that we can account for that variation that's being added in the outcome. The second reason we might want to is because randomization is already restricted within blocking level. So we can't do full randomization. We have to randomize within blocking level. We talked about a couple of these examples in class, but this is a second time where you should use blocks because that is what a blocking factor is. It's a limitation on that randomization in a variable that you don't particularly care about. Finally, looking at issue 3, where sometimes we have a choice, if you really don't care about that factor, but you want to account for it, you can use it as a blocking factor and randomize within it. I tend to not do this personally, and I think that there are some different options and different benefits and detriments within each one. So it really depends on the research context. But at least in my experience, typically what we'll do if we don't care about a factor, but it doesn't have to be randomized within the level of that second independent variable we don't care about, is we'll just treat that second independent variable as a true independent variable. It lets us do some other things with it, such as look at interaction effects, which we haven't talked about yet. And because it lets us do some other things with it, it is better, in my opinion, to include it as a second independent variable. Now, there might be some situations where it comes up where it would be better to randomize within the levels of that second independent variable. And in that case, you would want to treat it as a blocking factor. But the only time I would even consider that is if I genuinely don't care about that factor. That is, the effects of the different levels of that blocking factor are truly not of interest for the study. So typically we're going to be using blocks because of the first one. And again, think we can only get 4 coupons from each ingot. Our study requires 16 coupons, so we're going to be using 4 ingots. So we could either account for ingot as a blocking factor or not account for it at all and have that variability be added to the error variability. So that's going to typically be why we use a blocking factor when we're selecting one. And it's important to note here that a special case of blocking factors is this idea of a repeated measures design. In a repeated measures, we're blocking by individual. So we have one individual who does, say, 3 different tasks. Well, we would have that individual be their own block. And if we're trying to analyze the difference between 3 different tasks, we don't necessarily care about the different individuals doing the tasks. We just want to look at the tasks themselves. If you think about the exercise example that we had in class, in the exercise example, without even telling you, I randomized the assignment of tasks within each student. So in that case, it was treated as a limitation on randomization. We actually ended up doing a randomized complete block design in that design without even knowing it. So that's when you should be using blocking. When should you not be using blocking? So when the factor is of interest, we should not be using blocking, if at all possible. Now, sometimes it's the situation demands that the randomization is the randomization of a blocking design, and we kind of have to deal with that. But if at all possible, if the factor is of interest, we should not be using a blocking design. And the reason is because when we restrict randomization, then the blocking doesn't get to experience the full randomization of a completely randomized design. And that limitation on randomization can impact our conclusions about the different blocking factors. Now, I think you could think of a couple examples in doing this. This might end up being a homework question, but start to think through a couple of examples of how you could really play with the system of not having to randomize across blocking designs because you're randomizing within blocking designs. That can have some impacts. In the same way, just like if randomization has to happen within a factor level, if randomization can't happen within a factor level, then we're not using a blocking design. Remember, blocking is more than just a variable. It is a restriction on randomization in some meaningful way. So in this case, if we can't have that restriction on randomization, we're not using a blocking factor. What we'd call that is a second independent variable. Finally, we should not use blocking, and this isn't talked about. It is talked about in your book, but I don't think this is talked about often enough. Blocking is often treated as this, adding blocking factors is great, add as many as you can, blah, blah, blah. But if the blocking factor is unrelated to the dependent variable, adding a blocking factor into your design actually becomes harmful. So if the blocking factor is unrelated, then when we add the blocking factor, we're actually removing some of the degrees of freedom that are available and putting them in this factor that's completely unrelated. Because of this, this can actually increase our error rate. So the blocking factor has to at least account for enough variation to counteract the degrees of freedom that it's taking away. Otherwise, this will actually increase our error as opposed to decreasing it. Now, it has to be a pretty unrelated variable to increase error. Most variables, even, I guess not truly randomly generated variables, but most variables that even have a cursory relation to the outcome will tend to be worth putting in there. We can, of course, also test this and look at the size of this effect. But it is worth noting that you shouldn't just toss the kitchen sink into the model. If the blocking factor is unrelated, then you shouldn't be adding it because it's counterproductive. All right, so the randomized complete block design, we've been talking a lot about blocking factors up till now. What is a blocking factor? When do we use them? When do we not use them? Some different situations, and really getting into the meat and potatoes of what defines a blocking factor. But now we're going to talk about what this chapter is largely about, the randomized complete block design. Now, the randomized complete block design is well, first let's just take it in name order, randomized. So we are randomizing our data. Now, this is important to consider that this is a random design. First of all, I guess the other thing to consider, well, let's just kind of keep going in order. Complete, it's the second bullet point, and we'll come back to the first one. But the complete nature in randomized complete block design means that there are no missing values. So if you look, there's a randomized incomplete block design, or the balanced incomplete block design, the BIBD, balanced incomplete block design. This is in your textbook. You are welcome to check that out. I can't remember if we have notes on it or not. I guess we'll see. That we'll go over in class. I don't think we do. But in the randomized complete block design, the complete word means that we have all of the combinations between our factor, level, and block. And that takes us back to bullet point 1, that the randomized complete block design is a design that has a single independent variable and a blocking factor. So there are going to be 2 variables that we're accounting for on the right-hand side of the model and 1 dependent variable. So the 2 variables we're accounting for are the independent variable, that factor of interest, and the blocking variable, that blocking factor. And then we think both of these has an impact on the dependent variable. Remember, based on the previous slide, that blocking factor should be impacting the dependent variable. And if it's not, that's going to be a problem. It's going to increase our error rate. All right, so we can do randomized complete block design via fixed or random effects. I think we'll have like a slide on random effects, randomized complete block designs. So the randomized is not talking about fixed versus random. It's talking about the randomization procedure. So we're going to be using these randomization procedures in the randomized complete block design. That's what that randomized word means. Typically, we're going to look at this as fixed effects. That is, we want to fix the different effects in the blocks and the independent variable. You can do random effects. Again, we'll have a slide on it. Your textbook goes into this a little bit more. It's just not what we're going to cover. So at the bottom here, I have the chapters that talk about these really interesting things. I think the missing data, the balanced incomplete block design, or just I think the textbook talks about just missing data too. What do you do if you have just somebody forgot to take the measurement or the measurement got corrupted? How do you deal with the missing data? That the textbook talks about a bit. And then the random effects and blocking, we'll talk a bit about that again at the end. Note that when you get into section 4.1.4, this requires some experience with multiple linear regression. So you're looking at the full and the reduced models, and you're comparing full and reduced models. If you've taken the regression class, that should be old hat. You should be pretty comfortable with that. If you haven't taken the regression class, it's going to be a step above. You're welcome to check that out if you want to, but just be aware it's going to be maybe a little bit more difficult for you. So going into our first example here, excuse me. So this is an example from our textbook. We're talking about 4 different tips looking at the hardness rating on a hardness tester. So we're looking at these different system capabilities, and we're going to assign the tips to be an experimental unit, and we're going to be using the test coupons. Again, this isn't like the coupon from a grocery store. This is a small amount of metal that we're testing these different tips on. So we're looking at a completely randomized experiment, at least initially, but the coupons themselves are a source of this nuisance variability. So we might be looking at coupons with different hardness levels because different coupons maybe be being made out of different hardnesses or different pieces of metal. So different coupons might themselves introduce variability. So if we can control for that, that would help to reduce the error variability. Now note that this nuisance variability, we keep writing this term nuisance variability. What this means is that this is error. This is going to be in our statistical model error unless we figure it out. So it's not going to be error if we can account for it, but if we don't account for it, this nuisance variability turns into error, and that's kind of why it's a nuisance. So if we can account for it, that reduces our error term by the amount of this variability. So what we're going to do is each coupon, so we talked about cutting multiple coupons from an ingot. That's not what's going on here. We're going to use each coupon itself as a block. So think about like a big round piece of metal. That's our coupon. So instead of just like stamping one little hardness tester on it, what we're going to do is we're going to put like 4 corners on that little round piece of metal and do all 4 hardness testers on the same round piece of metal. So we're going to assign all 4 tips to each one of these coupons. So the coupon itself is actually going to be the block. So thinking about this, again, the coupon, and you can kind of look at the coupon, and if you can picture it yourself, picture a little slot on the top left, top right, bottom left, bottom right, where we're going to be trying this out. And so if you can picture this slot, we've got this little circle of metal, top left, top right, bottom right. We can randomly assign which of the tips are going to go into each of these points, but I can't take this little point on the coupon and randomly assign that point to another coupon. It doesn't really work like that. That's not really possible. So these coupons are going to be treated as a block because they restrict randomization. All of my experimental units, which are going to be these little points on these coupons, they can be randomly assigned to tip, but they can't be randomly assigned to coupon. All 4 of those on the first coupon are kind of stuck on the first coupon. All right, so when we're looking at the variability with blocks, variability between blocks can be as much as we want. And in fact, it's a good thing when variability between blocks is big. So variability between blocks can be large. When my coupons are really different, then the blocking factor actually becomes a really, really good thing to account for. That means that each of these different pieces of metal gave a very, very different response. So it's going to have a lot of variability. Now, if I wasn't accounting for coupon, all of that new variability would go straight to the error term. But because I am accounting for coupon, it's going to all go into this coupon term, and that's going to be a great thing. We like that because we're accounting for this in the blocking factor. Variability within a block, though, should be relatively small. So that is my 2 coupons, coupon 1 and coupon 2 can be very different. But when I'm looking at all 4 of the different corners in the coupon, that shouldn't be all that different. So when I'm looking at the different observations within the coupon, I want that to be very, very, very small as possible. So that is that when all 4 tips are stamping each of the corners, that the tips are stamping virtually identical things. We could pretend that they're all the exact same. So we've got our block in general being a specific level of that nuisance factor, and the complete replication is based in each block. So each block is, each coupon here is going to be the, each coupon here is going to have all 4 of the tips being stamped on it. So each of these single coupons are each of our blocks. That's what we mean block is a specific level. We're going to call each one of these things blocks. And this coupon variable is called our blocking factor. So we're going to block on coupon. Again, we talked about the restriction on randomization, but what we didn't talk about quite yet, and we've talked about previously, is that all runs within the block are going to be randomized. So what we're going to do is, given these 4 slots on this coupon, we're going to randomly assign the order of which tips are going to go where. So tip 2, tip 1, tip 3, and tip 4 might be how we approach that. And then we're also going to randomize what order they're run in. So here we can see we've got test coupon 1, test coupon 2, coupon 3, and coupon 4. Again, when I tend to design this, this is a great table to look at the randomization, but not necessarily for the data. So this is a great way that we look at the randomized order, but this wouldn't be how we would structure this to look at data. This would be extremely confusing, right? So if we wanted to structure this based on data, I might have the blocks, block 1, block 2, block 3, block 4 as each of the rows, and then the tips, tip 1, tip 2, tip 3, tip 4 as each of the columns, and then I would enter my data into that as appropriate. But that wouldn't, if we did that, oh my gosh, excuse me, that wouldn't, if we did it that way, measure the, or demonstrate the random order that this should be run in. So this is a great way to demonstrate the order in which we're running our experiment. One other thing we should note here in looking at this is the two-way structure of the experiment. So we've got now 2 variables that we're interested in how they affect the dependent variable. We've got the coupons and we've got the tips. Now the coupons are a blocking factor, but they're still a variable that we're interested in how that variable affects the dependent variable. In this case, we're only interested so that we can remove that variability when we're studying the relationship between the tip and the dependent variable, but it is still something that we're studying, and that makes this a two-way structure. In many ways, you can really think about this as a one-way ANOVA. This is different, definitely, so you could also think about this as a two-way ANOVA because of this two-way structure, but we're really just looking at the relationship between tip and the outcome after accounting for this blocking variable. So the randomized complete block design you can think of as a one-way, as an ANOVA that's also accounting for this blocking factor. And incidentally, the way we account for this blocking factor is to extend our ANOVA. So that's been the follow-up on our initial discussion on blocking factors. In the next video, we'll discuss how do we include blocking factors in the analysis. So how do we extend that one-way ANOVA to now account for these new blocking factors?